In this series of lessons, we're going to be looking at limits as x approaches positive or negative infinity, and also limits where we get infinity or negative infinity as our limit. Right? So first of all, we're going to look at finite limits as x approaches positive and negative infinity. So the symbol for infinity does not represent a real number. We use infinity to describe the behavior of a function when the values in its domain or range outgrow all finite bounds. For example, when we say the limit of f as x approaches infinity, we mean the limit of f as x moves increasingly far to the right on the number line. When we find the limit of a function as x approaches infinity, we're determining the value of the function is approaching as x gets increasingly larger. When we say the limit of f as x approaches negative infinity, we mean the limit of f as x moves increasingly far to the left on the number line. When we find the limit of a function as x approaches negative infinity, we're determining the value the function is approaching as x gets increasingly smaller. So how can we evaluate a limit as x approaches infinity? There are three ways to estimate or evaluate the limit of a function: numerically, graphically, and analytically, using algebraic techniques and properties of limits. And let's see how we can use these techniques with limits at infinity. And we're going to start with numerically and graphically. So infinite limits and limits at infinity. The purpose of this lesson is to determine infinite limits, evaluate limits at infinity, and locate vertical and horizontal asymptotes. So let's look at a numerical approach. So a limit as x approaches infinity. So let's investigate with a table of values. Right? So here, and some of my commas look like periods, because, well, I accidentally typed period instead, because it looks really, really similar when I'm looking at the board sometimes, the keyboard sometimes. All right, so we plugged in 100 in for all the places we saw x, and we got 2.51003. And if you plug in 1,000, you get 2.5010. And if you plug in 10,000, you get 2.5001. If you plug in 100,000, you get 2.50001. If you plug in a million, you get 2.500001. If you plug in 10 million, you get 2.50000001. If you plug in 100 million, 2.50000001. And finally, a billion. So notice what's happening each time. What happens is x becomes increasingly larger. What does the limit appear to be? So notice we keep seeming to get closer and closer and closer to the number, the finite number 2.5. That appears to be our limit from our table of values. And let's take a look at, now we're going to go to negative infinity. All right, so what happens as x becomes increasingly smaller? What does the limit appear to be? So we plug in negative 100, we get 2.49002. Plug in negative 1,000, you get 2.49902. You plug in negative 10,000, 2.4999. Plug in negative 100,000, 2.49999. Plug in a million, you get 2.499999. There we go, those are commas. Plug in 10 million, 2.4999999. 100 million, 2.4999999. And then finally negative a billion. Right? So notice we're just getting more nines, right? Getting a little bit more and a little bit more and a little bit more. We're seeming to be like we're getting closer and closer and closer to the finite number 2.5. So at least from our table of values, it appears that our limit as x approaches positive infinity of this particular function, and the limit as x approaches negative infinity of this particular function, appears to be 2.5. Let's look graphically. Right? So here we can see the left-hand side and the right-hand side, and my graph is blocking. There we go. So does the limit from the graph appear to support the results we got numerically? Right? Notice our graph seems to be leveling off. And so it's not as easy to see the values here because these are going up by 5. But it does appear to, like we're leveling off about halfway in between 5 and -5. I think there might be a box over here. So as x approaches negative infinity, y appears to be approaching 2.5. And as x approaches infinity, y appears to be approaching 2.5. So graphically as well, it appears that the limit as x approaches negative infinity of f of x is 2.5, and the limit of f of x as x approaches positive infinity appears to be 2.5. Right? So limit of both as x approaches negative infinity and as x approaches positive infinity, from our graph anyway, appears to be 2.5. So a little reminder of a formal definition of a limit. So let f of x be defined at an open interval about c, except possibly at c itself, right? Because the value of the function, our function does not have to be defined at a point, so long as we're approaching the same value from the left-hand side and the right-hand side. So we say that the limit of f of x as x approaches c is equal to L if the absolute value of f of x minus L becomes arbitrarily small when x is any number sufficiently close but not equal to c. And if you don't remember what all that means, remember I did a podcast where we did nothing but go over the terminology in the formal definition of a limit. Right? So if you get confused by the definition, just take a look at that podcast. Right? Just review that. I'm trying to remember which lesson that was in. I think it was with the graphical limits. So yeah, graphical limits is where I put that. So just review that. And of course I can do another proof for you in class. But we're looking at limits at infinity, so let f be a function defined on some interval from a to infinity. Then the limit of f of x as x approaches infinity is equal to L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. More precisely, the limit of f of x as x approaches infinity equals L for every number where epsilon is greater than 0. So every time that our absolute value here of f of x minus our limit, right? If this difference here is less than epsilon, there's got to be some number that what we're getting. Let me say this again. So there's got to be some value of x. That's what I'm trying to say. As x is getting larger and larger and larger and larger, that this difference between the function and the limit is getting smaller and smaller and smaller, right? So the larger the x value, when we're talking about a limit as x approaches infinity, right, the smaller the difference between the function and the limit. In other words, the value of the function is getting closer and closer and closer to the limit. So just a tad bit different than when we were approaching some finite number. Oops, where'd it go? There it is. Sorry, I went too far. Right? So when we're approaching some finite number, right, we're getting closer and closer to our x value, right? So as the difference between c and x got smaller and smaller, the difference between f of x and the limit got less and less. Now, because the limit is going to infinity, as x is getting larger and larger and larger, the difference between the value of the function and the limit is getting smaller and smaller and smaller. Right? So that's all it means when we're looking at a limit at infinity. And likewise, if it's a limit of f of x as x approaches negative infinity, or I have n in there, as x or n, whatever variable you like, approaches negative infinity, right? and so let our function is going to be defined on some interval, negative infinity to 0. Then the limit of f of x as x approaches negative infinity equals the limit means that the values of f of x can be made arbitrarily close to L by taking x sufficiently small. More precisely, the limit of f of x as n approaches negative infinity equals L for every number where epsilon is greater than 0. There exists some corresponding number greater than 0 such that for all x, such that the difference, the absolute value of the difference between the value of the function and the limit is less than epsilon for all x whenever x is smaller than n. All right, let's talk about what this means. All right, so now we're heading to negative infinity. So, and I'll write it on the other page too. So as x, so here's my kind of informal explanation. As x gets smaller and smaller, so it's decreasing without bounds, the difference, so it goes this way, the difference between the value of the function and the limit gets smaller and smaller. Let's take a look at that, and you can pause if you need to pause, but let's take a look at that in reference to as x approaches infinity. So here, as x gets larger and larger, and because x is increasing without bounds, it goes this way. I just want to write it underneath this part. The difference between the value of the function and the limit gets smaller and smaller. Let's see if that makes sense. If we look at the limit we just did. All right. So let's go back to this limit here, and I want to look at the graph. So we'll look at the positive. So notice as x is getting larger and larger, the difference between the limit and the value of the function gets smaller and smaller. Right? So if I'm only at 100, right, if I subtract, right, so the value of the function here is 2.51003, and the value of the limit we said appeared to be 2.5. Right? So that difference there is 0.01003. If we come way over here, where we're plugging in a billion, right? So we've got 2.500, the value of our function would be 2.500000001, and our limit appears to be 2.5, and I have no place to write now. If we take that difference, that's going to be 0.00000. Wait, 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros, and a 1. All right, so let's look at the difference, all right? So as x is getting larger and larger, notice that difference is getting smaller and smaller. I'll write that better. So many zeros. There we go, all right? So definitely 0.00000001 is smaller than 0.01003. So notice that difference is getting smaller and smaller and smaller. And that's basically what that formal definition applied to limits at infinity is just saying. And the same thing over here, right? If we take the difference between 2.49002 and 2.5, that's going to be 0.0. For some reason it's harder for me to go this direction. It was easier, well, it makes sense, but it was easier to subtract the smaller numbers. Or when we had numbers that were a little bit bigger than 2.5, then a little bit smaller than 2.5. But 0.00, I'm just too linear. 2.49002. So it's going to be 0.0002. I was right the first time. Oh, it was 8. Sorry. 0.0008, right? Because this would be a 10. And actually then that would make all of these things 9s. I take that answer back. So 0.09, right? Because these are now going to be 9s as we're taking 1 away. And then this would be a 4. Yes. So 0.0 or 0.09998. There we go. I can subtract. And if I add I still don't think, oh no, that was a 9 over there. Oh my gosh. Well, when it gets to be late, 2.51000, just put a 0 there. 2.49002 shouldn't be that difficult. This would be an 8. That would carry over to be a 9. This would be a 9. I was missing a 0. There we go. So I knew something looked wrong. 0.00998. Yay! There we go. All right, and over here, if we take the difference between the value of the function, which was 2.499, 1, 2, 3, 4, 5, 6, 7, 8 9s. 1, 2, 3, 4, 5, 6, 7, 8 9s minus 2.5. That's going to be 0.0 and a whole bunch of 1s, right? Or a whole bunch of zeros. Now I don't trust myself. 1, 2, 3, 4, 5, 6. 2.499. The smart thing would have been just to grab a calculator. It really should not be this difficult. Go the other direction. All right, so this is going to be a 10, so that's going to be a 1. Right, so it's going to be a bunch, and then these are going to be 9s all the way through. So it's going to be 0.0000000, all zeros, and then a 1. 0.0000. 2, 3, 4, 5, 6, 7, 8. I think it's something like 9. All right, something like that. All right, I won't swear that I didn't make an error here somewhere. However, you get the idea that as x was getting smaller and smaller or larger and larger, when we're looking at a limit as x approaches infinity, we're getting that difference is getting smaller and smaller and smaller. And if I have a math error here, we'll just go with it. But however, you get the idea that definitely that 0.000001, that is much smaller than 0.00998. Right? So let's continue looking at limits at infinity. so now here's a visual representation of that. So the limit as x approaches infinity means, so the limit of f of x as x approaches infinity equals L, means that for all epsilon greater than 0, right? So if we're looking at differences greater than 0 between our value of our function and our limit, there exists some number that as x gets larger and larger, we're getting closer and closer and closer to that limit. And it works the same way, whether it's x approaches infinity or x approaches negative infinity, right? The larger the number, the smaller the number, depending on whether it's infinity or negative infinity, right? The smaller the difference between the value of the function and the limit. All right, so let's take a look at this one here. So it's, as x approaches infinity, here's a trig function. So, and we're going to look at a numerical and a graphical. So let's investigate the limit with the table of values. I'm not going to read all of those because there are a heck of a lot of zeros. All right, so you can read as x approaches 100, 1,000, 10,000, 100,000, and every single one of these we're going to be having periods instead of commas. 1,000,000, 10,000,000, 100,000,000, and 1,000,000,000. Right, so notice that it's kind of flip-flopping a little bit, right? So we got positive, positive, then a negative, negative, positive, a negative, a negative, a positive. So we're kind of flipping signs a little bit. But what do you notice about the numbers? Get more and more zeros in there. Our numbers are getting smaller and smaller and smaller. Sometimes they're above the line, sometimes they're below the line, but it looks like maybe that limit is approaching 0. Right? How about as we go to negative infinity? Again, bopping around a bunch in the signs, but notice the numbers are getting smaller and smaller and smaller. Appears like the limit of cosine x divided by x as x approaches negative infinity might be 0. And actually, let's see if that makes kind of intuitive sense. How much can cosine change? So cosine's kind of limited, right? It doesn't have a whole big range of values, right? 1 to negative 1, right? So that numerator is not changing very much, right? Sometimes it's positive, sometimes it's negative, but it's not changing very much. And the denominator is getting larger without bounds or smaller without bounds, depending on whether, so here it's increasing without bounds, and here it's decreasing without bounds, and cosine x is not changing a whole lot. So if you got something that's really not growing very much, divided by something that's growing very, very, very much, it's like you have a cake and you divide it up into 1,000,000 pieces. The amount of cake you're going to get is going to be pretty small, kind of like nothing. So let's take a look at the graphs here and see if the limit from the graph appear to support the results that we got numerically from the table. Right? So if we look to the left, the limit of cosine x over x as x approaches negative infinity. Notice the line does go above and below the line, but notice it seems to be getting, that above and below part is getting smaller and smaller. And that graph seems to be getting closer and closer to the x-axis. Likewise, if we look at the limit of cosine x over x as x approaches infinity, again, it crosses that the x-axis, but notice it's getting closer and closer to the x-axis. So the limit graphically appears to support the limit we got using a table of values. Here we have another one. So we're going to look at the limit with this table of values. And in some ways, this limit and this limit are the same. Some ways are different. All right, so we have the limit of 1 over as x approaches infinity. 1 over x as x approaches infinity. All right, so this is really easy for me to do in my head because I'm literally just dividing by 10 each time. So you can see we're getting more and more and more zeros here. These numbers are getting smaller and smaller and smaller, right? Certainly, a millionth of something is a lot smaller than 100th of something, right? So it appears that our limit is going to 0 when we look at our table of values. How about as x approaches negative infinity? Now all the values are negative, but again they're getting closer and closer and closer to 0. They're not getting smaller and smaller, right? But they're just getting closer to 0. So it's already on the negative side. So technically, 0.01 is a smaller number than negative 0.00 whatever there, because it's a negative, but we're getting closer and closer to that x-axis, closer and closer to 0. Let's see if the graph supports that. So here is our graph, right? So we have the limit as x approaches negative infinity limit as 1 over x as x approaches negative infinity. We see that on the left-hand side, our graph is getting closer and closer to the x-axis. And again, on the right-hand side, the graph is getting closer and closer to the x-axis. And technically, by the way, when you're taking the limit as x approaches positive infinity or negative infinity, it is a one-sided limit, right? You can't have something that's smaller than negative infinity or greater than infinity. So it's just understood that this is going to be a one-sided limit, coming from one direction. So that's where I'm going to stop, because the next lesson is going to be analytic properties, right? So that's the end of numerical and graphical. And let me know if you have any questions. Thanks for watching. Bye for now.